morning, students. So in the last class we derived some expressions based on the Gauss Law, the intensity of electric field due to different objects, and in almost all the calculations we consider uniform distribution of the charge. That means whether it is surface density or it is volume density, we consider the uniform charge density. I hope all of you understood those derivations. And so with those derivations, now we should get an idea how to apply the Gauss law. Whether it may be uniform distribution of the charge or whether it may be non-uniform distribution of the charge. So how to apply the Gauss law, that idea you should get. And so now with that idea, now we are going to solve about this some problems based on the non-uniform charge distribution. So write that. So in a sphere of radius r, the charge is varying according to the expression rho is equal to, charge density is varying according to the equation rho is equal to rho naught into 1 minus small r by capital R, where rho naught is positive constant and small r is the distance from the center of the sphere. Center of the sphere. Find an expression for that is the first question. That means intensity of electric field when R is less than R. That means inside, you can write, find the intensity of electric field inside and outside when R is greater than R. And also find the E maximum. That means maximum intensity of electric field. And we need to find where that intensity becomes maximum. So these are the calculations required for this. So then charge density, volume charge density is varying according to that equation. So we need to find intensity of electric field inside, outside, and the maximum value we need to find. Suppose I am taking first of all the inside calculation here. So when inside calculation is, suppose if you want to find intensity of electric field at this point, right? Then we need to consider a Gaussian surface here with R as a radius. And then this is the element what we are considering here. Small element of radius r and thickness dr. And so first I am calculating this. Then just let us write the Gauss law. So by using this Gauss law, we can write this as flux is equal to the surface integral of E bar dot dA bar is equal to 1 by epsilon naught times charge enclosure, right? Now this charge enclosure is nothing but, now let us see first I am doing this like left hand side calculation. So left hand side calculation is here we consider a small element of area here, then electric field will be along this direction E, and because it is a positive charge and the A bar is also, we know it will be radially outwards, right? And so now these two are along the same direction. So I can write this as integral of E into dA into cos 0 we can write. So which is q in by epsilon 1, right? And now this term I can write as E into integral of dA, that is equal to q in by epsilon 1. Or this is E into 4 pi small r square, the total surface area of this element you will get. This is q in by epsilon 1. Let's suppose this is our equation 1. And so now in this we need to calculate this q in value, the charge enclosed by the Gaussian surface. So therefore this charge enclosed by Gaussian surface, we can write it as the charge enclosed by the Gaussian surface is nothing but Qn is equal to integral of rho into dV we need to write. Because in the previous problems or in the previous derivations, Qn means just we mentioned as if rho is uniform charge density, then rho into the volume of the element you can write. That is in our previous calculation, like uniformly charged sphere if we consider, then we mentioned just like rho into charge density into, directly we mentioned like volume. But here since it is a variable here, the charge density is variable, we need to take a small element and then we should write the integration here. And so that is nothing but I can write this as q Q is equal to integral of rho naught into 1 minus r by r into, now this dV is nothing but volume of this spherical element. The small element for this charge we need to write here, the spherical element I am writing. The spherical element is nothing but 4 pi r square into dr. This is the volume of the spherical element. Surface area 4 pi r square is surface area, dr is the thickness. So that surface area and thickness will give the volume of the element. You can't write totally this volume of this sphere 4 by 3 pi r cube, you can't write because charge density is not constant here, charge density is variable. And so then now we need to write this integration. As we are finding our actually we are solving the first part here. First part means we are finding this inside. Inside is nothing but r less than r. And so now we should integrate this from 0 to smaller. Therefore this is from 0 to I can write this constants outside rho naught into 4 pi into, here integration is r square minus r cube by r dr. This is from 0 to r. So therefore this Qn is equal to rho naught into 4 pi by, integration you can carry out here. This is r square integration is r cube by 3 and here r cube integration is r power 4 by 4, right? So I can write this as r cube by 3 minus r power 4 by 4r. So now that is the charge enclosure there, right? I can take this r square common. So rho naught into 4 pi r square I am taking common. For r cube you can take common here. If you take r cube common, then it is 1 by 3 minus r by 4r unit, right? Now that is charge enclosure. So substitute this charge enclosure in this equation here. Therefore from equation 1, so then E into this is E into 4 pi r square is equal to 1 by epsilon naught times into rho naught into 4 pi r cube into 1 by 3 minus r by 4r. So then 4 pi here r square you can cancel here, so that this finally you can write this intensity of electric field inside as rho naught by epsilon naught into, here one r will be there, r I am writing inside, so r by 3 minus r square by 4r. So this is the intensity of electric field inside this spherical charge distribution here. Got it? The same procedure as that of our previous calculations. The only difference is we need to calculate this Q in value here, charge enclosure. So in the previous also we calculated that, but generally we write there as rho into, directly we write volume of this sphere if you want to write. Then rho into 4 by 3 pi r cube we can write if the charge density is constant. But here the charge density is variable, so we should write this integration by taking the small spherical element. Then we should integrate that. So then if you integrate this, then this is the expression what we are getting here, right? So that is the expression for inside. So similarly, let us see for this outside here. So I will write the expression for the inside here, so that we can find this maximum value. So rho naught by epsilon naught into r by 3 minus, so this is r square by 4r. So this is our inside expression. Now similarly, let us see this our outside calculation here. So for outside also actually everything will be same only. Just in the Q in calculation, just we need to change the limits, right? So let us see this. Now this is the second part we are calculating. Outside, small r is greater than r, right? So when small r is greater than r, we can write this as, this total calculation will be same. Just we need to change the diagram also. So I will draw this another diagram for this outside. And this actually our diagram should be like this. Suppose this is the sphere of radius r. Now we need to take a Gaussian surface outside this. That means if you want to take it, if you want to find the intensity of electric field at this point, the distance r from the center, then we need to take a Gaussian surface passing through that point, right? So then this is our r. Then here also we consider a small element here, the area element dA. then intensity of electric field will be like this and dA vectors will be like this, right? And so both are in same direction. So this calculation is same, and this part will be same in our all derivations also, right? So that means we take such an element here like then d into E into dA cos 0, then E is constant that we can write outside, then E into dA you get, the dA is nothing but 4 pi r square. So up to this there is no change, again we need to write the same calculation. Next here, charge enclosed by Gaussian surface. So the same calculation is q in is equal to integral of rho into dv. Just here when compared to our previous calculation, we need to change the limits. So therefore this is q in is equal to integral of rho naught into 1 minus into 4 pi r square dr. The same. It means here also we cancel a small element here. For this first, for this we write this element charge enclosed in this element, and so then volume of that element we are writing here. That means 0 to that means 4 pi r square is the surface area of this element, and into dr is the volume of this element here, right? And so now that limits we need to consider here. Charge enclosed between the Gaussian surface. This dotted line is dotted sphere is our Gaussian surface. Now you can't integrate from 0 to r because our r is greater than this capital R, and so our charge distribution is only from center to this capital R only. This in this space there is no charge here, and so that we need to integrate from 0 to capital R. And so this is rho naught into 4 pi into integral of r square minus r cube. This is r cube by r dr. Now limits are from 0 to capital R. Therefore this q in is equal to rho naught into 4 pi into, this will be r cube by 3 minus here r power 4 by 4 you will get. When you substitute here r power capital R power 4, then you can cancel this capital R, and so then this is also r power 3 by 4 you will get finally after cancelling this denominator r. And so now you can simplify this further. Rho naught into 4 pi into, if we take LCM here, then this will be r cube by 12 unit, right? And so now I can substitute this q in value in this equation in our Gauss Law equation, and therefore from equation 1 you can write this as E into 4 pi r square is equal to 1 by epsilon naught into rho naught into 4 by r cube by 12. So then this 4 pi and 4 pi you can cancel, and therefore I can write this intensity of electric field outside the sphere as rho naught into r cube by rho naught into r cube by 12 epsilon naught r square. So right. So that is our outside expression. Got it? The inside and outside are almost the calculation will be similar. The only difference will lies here in these limits. So the limits we are changing, we need to change from 0 to r. When you are changing the limits from 0 to r, then automatically here this charge calculation, charge enclosed, you will get some different expression when compared to our inside calculation. So that is our outside expression here. So I will write this expression here. So therefore this outside is equal to rho naught into r cube by 12 epsilon naught into r square into it. This is our outside expression. Next in this we need to find this maximum field. We need to find the maximum intensity of electric field. Now just by identifying, observe those two expressions, and where the field is maximum you will get an idea whether the field is becoming maximum inside the Gaussian surface or inside the sphere or outside the sphere. Just by seeing those expressions you can conclude that. So just if I observe the outside is rho r cube by 12 epsilon naught r, right? That indicates the field is decreasing with r square, that is inversely proportional to r square. So that the field, there is no chance of becoming maximum here. The field outside the sphere, the field goes on decreasing. When this r value is increasing, it goes on decreasing. So there is no possibility to get the maximum value outside. The possibility is there for this inside here. So then if E is maximum, then we know that its differentiation should be equal to 0. Now whether we need to differentiate this term or this term is, that is nothing but what we are computing here. The field only, there is possibility for the maximum only this inside, because it is a continuous decreasing function. This outside is, and so that I am going to differentiate this inside expression here. So this d by dr of rho naught by 3 into r by r cube minus r square by 4r. This is equal to 0. Now differentiate that rho naught by, sorry, this is epsilon rho naught by epsilon naught into the differentiation of this r is 1, so 1 by 3 into 2r by 4r unit. So this is equal to 0, right? And so that I can write this as 1 by 3 is equal to r by 2r, and therefore this r is equal to 2r by 3. That means at a distance of 2r by 3 from the center, the field is becoming maximum. At this distance, sometimes they may ask about this distance also, where the field is becoming maximum. So then this is the distance where the field will become maximum. And then let us write the now maximum value here. So just to calculate the maximum value, we need to substitute this r value in this equation. So I can write this as rho naught by epsilon naught into 1 by 3 into r is 2r by 3 minus 1 by 4r into r square, 2r by 3 whole square. Right? Just by substituting r value in this equation. And simplify that, you will get this maximum value here. So rho naught by epsilon naught, this will be 2r by 9. So then this is r by 9. Right? Here 4r square you will get, then 4r will be cancelled, and only this 3 square will be 9 will be there. And therefore this E maximum value I can write as rho naught into r by 9 epsilon naught. So this is the maximum electric field. So it is a way of finding this maximum electric field here, when the field is, when the charge density is variable. So that is, we can find inside or we can find outside, and we can find the maximum values like this, right? So note this. Now let us go to another example based on this non-uniform charge distribution. So write another problem based on this. A spherical ball of radius r, capital R. A spherical ball of radius capital R is having uniform charge distribution. Is having some uniform charge distribution. The surrounding medium is having the charge density varying with the distance from the center of the ball, as, write the expression rho is equal to alpha by r. In brackets, alpha is constant. That r is nothing but distance from the center. Assume permittivity of the ball and the surrounding medium is unity. Assume permittivity of the ball and the surrounding medium is unity. If, now write the question, if intensity of electric field outside the ball is independent of distance of the point from the center of the ball is independent of distance of the ball from the center of distance of the point from the center of the ball. Find charge enclosed by the ball. Find charge enclosed by the ball. So that means here this is a ball of radius r. It is having some charge. Let's suppose I am taking this as some charge issue. It is given as uniform charge distribution, right? Now the surrounding medium is also having some charge density. Now this charge density is varying like this. Now suppose if I am taking a point here, then we need to take a Gaussian surface like this, right? This is our capital smaller. Now the given condition is at this point the intensity of electric field is independent of the smaller. So if it is independent of the smaller, we need to find this Q value, the charge enclosed by this ball here. It's actually a previous question, an important question. So say this. So again our usual Gauss Law application. So that means by using Gauss Law. So by using Gauss Law, I can write integral of E bar dot dA bar is equal to 1 by epsilon naught times the charge enclosed QE. And so now here again same, we consider a small elemental area here, and this is our dA bar, and E bar will also be along the same direction. So for spherical surfaces, generally we will get such a condition. So if it is a Gaussian surface is a cylindrical like our previous derivations, then for some surfaces maybe flux may be 0, and for some surfaces maybe flux may be non-zero values will be there. But spherical surface is almost you will get like this one. So now we can write this side. So like E into dA into cos 0, this is equal to 1 by epsilon naught times the Q plus some Q dash or small q I am taking, where small q is the charge present in this region, right? Now the charge present within this Gaussian surface is two parts. Let Q be the charge present in this ball, and small p is the charge contained in the surrounding medium. That means from capital R to small r. In that region, in this region, some small q is there. That is we are assuming here. First you may mention that let capital Q be the charge given to the charge contained in the ball. So we need to find the expression for capital Q only, right? So now this is our equation. So E into 4 pi r square this side, that will be equal to 1 by epsilon naught times Q plus Q. So suppose this is equation 1. So now we need to calculate the small q value here. That means you may to substitute in this equation. So that q value we can calculate from by using this equation. Charge enclosed in shell of inner radius capital R and outer radius small r. Got it? That means this we are taking as a shell. Now we are going to calculate charge enclosed within this shell here of inner radius small capital R and outer radius smaller. So that is our calculation here. That means we are going to calculate this Q value here. Therefore, that Q is nothing but integral of rho into dV. This dV is dV meaning is same. We need to take a spherical element, and that volume of that spherical element we need to write here. So I am substituting those values directly. So that means this rho value is given as alpha by r. This dV value I am directly substituting like our previous problem, 4 pi r square into dr. Right? Now the limits are according to this. Our limits are from capital R to small r. Got it? We need to integrate from r to r1. So now let us simplify this. So then 4 pi alpha into this r and r will be cancelled. So this is nothing but r into dr from capital R to small r. Therefore Q is equal to 4 pi alpha into r square by 2 you will get. So r square minus r square by 2. So therefore this Q is nothing but 2 pi alpha into r square minus r square you will get. And let us substitute this value in this equation here. Let us substitute this value in this equation in the first equation. So from equation 1, E into 4 pi r square is equal to 1 by epsilon naught times q plus 2 pi alpha into r square minus r square, right? And this, from this I am writing this E is equal to, so I can write this term as q plus 2 pi r square alpha minus 2 pi alpha into r square by 4 pi epsilon naught into r square. So now let us separate these terms here. So just I am separating the terms, like I am writing this as the first term here. So then if you cancel this 2 pi r square term, you can cancel here in this. Then you will get like alpha by 2 epsilon naught, right? Plus this nothing we can cancel here. So I am writing that as a one term here, 2 pi alpha r square by 4 pi epsilon naught r square, right? Suppose this is our equation 2. So now let us come to the given condition. Our given condition is, now this is the intensity of electric field at a distance r from the small r from the center of the ball and outside the ball, right? Now the given condition is, this expression must be independent of the small r. This expression should not depend on the small r. That is our given condition. So I will do the remaining calculation here. So the given condition is E is a constant. That means it should not depend on this. Therefore, it is possible, that means E value is constant when this term is 0, right? Otherwise, if this term is not 0, this is already a constant value. Alpha is a constant that is given, then we know 2 epsilon naught is also a constant value. Then this term, if this term is constant, if this term is 0, then automatically electric field will become a constant. If this term is not 0, electric field will be variable, because here r square term, small r square term will be there. And so that given E is constant, that is possible only when q minus 2 pi alpha r square is equal to 0. Or we can write this, q is equal to 2 pi alpha into r square. So now this is the charge enclosed by this ball here. So that is now our answer. So the charge enclosed by this ball is nothing but given by this expression here, right? So that is our calculation of this. So that means just we are applying the Gauss law, and in Gauss law we have two types of, that means two charges over there. One charge is charge contained within the ball, and the next one is charge between this capital R and the small r. So that we need to calculate according to the given variation here, given density. And then if we substitute in this, finally we are getting this expression. This E term must be constant, that is given condition in the problem. Then this term should be 0. Just we are equating this term to the 0. Then you will get that expression for this Q value here, charge contained within this ball. Note that. So I will give two problems based on this. Try those two problems. Not that. The charge density, the volume charge density in the space varies according to the equation. Rho is equal to rho naught into e power minus alpha r cube. The charge density in a space varies with the distance r, as rho is equal to rho naught into e power minus alpha r cube. And where the rho naught is constant and alpha is constant. Find intensity of electric field. Find intensity of electric field at a point at a distance smaller from the charge distribution, center of the charge distribution, at a distance smaller from the center of the charge distribution. Also write the expression for electric field Also write the expression for electric field when R is very small and R is very large, or I can express that as alpha R cube is very much less than 1, alpha R cube is very much greater than 1. That means when R is very small and R is very large, we can express like that. So that is one problem. Write another problem. This is there is no any sphere or anything here. Throughout this space, that current density is varying like this. That means if you are taking, suppose this is the Gaussian surface we are taking here. This directly you can take this as R here. Then limits we need to integrate from 0 the charge enclosure. While we are calculating charge enclosure, we can integrate from 0 to smaller here. There is no any other another object here. And next here, next problem. This is sphere of radius r. The charge density in a sphere of radius r. The charge density in a sphere of radius r varies with the distance from the center of the sphere. Varies with the distance from the center of the sphere. That is smaller in brackets, as rho is equal to rho naught into r. Then find the expression for intensity of electric field. Find the expression for intensity of electric field inside and outside the sphere. Inside and outside the sphere, right? The similar to that of the first problem, then just the function is different. So try these two problems here. So next I am going to the another important concept or another important application, this Gauss Law here. That is about this electric field in the cavities. So electric field in the cavities calculation is very important, and there will be a lot of problems based on this. And actually this cavity problems we also solved in our say gravitation. In gravitation also we calculated the gravitation field inside the cavity, right? Just all the calculation, the total calculation will be similar to that. Electric field inside a spherical. The density of electric field inside a spherical cavity, right? So now in this we can write this as suppose I am taking a spherical cavity is present inside a sphere of radius say AA. So this is a sphere of radius A having uniform charge density rho. Now in this a spherical cavity is present here. This radius of this cavity is suppose say B. And now the distance is the center C1 and this is the center C2, and so then this distance I am taking as some C, right? And so now this is total, it is having some positive charge density here. This total ball is having some positive charge density. So in this a cavity is made like this. Now we need to calculate intensity of electric field at any point inside this cavity. So first write the description about this diagram. Consider a sphere of radius A. Consider a sphere of radius A having uniform charge density rho. Having uniform charge density rho. A spherical cavity of radius B is made inside it. A spherical cavity of radius B is made inside it such that the distance of center of cavity from the center of the sphere is C. We need to find intensity of electric field at any point inside the cavity. At any point inside the cavity, let us say P. That means at the point P we need to write the intensity of electric field here. And for this we know the intensity of electric field inside the solid sphere at any point we can write it as, actually it is q by 4 pi epsilon naught into r cube into small r. And we know this you can write in terms of charge density. So if I write in terms of charge density, then it will be rho by 3 epsilon naught into r you will get, right? This is our intensity of electric field inside this. So now this expression we need to write in vector form here. In vector form if you are writing the intensity of electric field inside, we can write this as rho by 3 epsilon naught into r cube, sorry r bar, right? So that the electric field will be in the direction of r bar if this charge is positive charge density. If this charge density is negative charge density, then it will be opposite to that. Then here we should take it as negative sign here in case of negative charge density. So here it is a positive charge density. So if you solve the problem in terms of this charge density, then calculation will be easy for us. Even though in the problem if q is given to you, then convert that into rho only. And in terms of rho, you can write the charge density expressions more easily. And so now let us come to this calculation here. Now here, this calculation we can solve it in two different ways. And that means one approach is like we consider this as a total sphere without any cavity here. So without any cavity, we assume this total sphere like this. This let it be a sphere of radius say a, right, without any cavity. Next, instead of that cavity, we assume an opposite charge density here. Suppose this is sphere of radius b having this minus rho charge density. So this is plus rho and this is minus rho. Now we assume that this sphere of radius, that means sphere of radius b having this charge density minus rho is assumed to be placed inside this. That means in this place. That sphere of radius b and having minus charge density is assumed to be placed in this region. So if you place in this region, that is assumption. If you are placing inside this, the net charge is initially this charge is the charge present here is positive like this. So this is actually that place here. Now we are placing that negative charge here, same amount of negative charge. And so that net charge in that region will become 0. So net charge in that region is becoming 0 means it is nothing but equivalent to a cavity. No charge is present in that region. And so now that means this results as a sphere with the cavity here. So then that is the resultant here, right? That means we can assume like this. We can assume like that. And so now the resultant electric field at that point we can write as electric field due to the positive charge density due to the whole sphere plus electric field due to this negative charge density here, right? And if you add those two vectorically, then you will get the resultant electric field at that point. So that is one approach. We can assume total sphere is positive charge density, and then wherever the cavity is present, that cavity space or the cavity volume we consider it as a negative opposite charge density there. So when we combine them, that results as our cavity there. And so that the resultant electric field at any required point is a resultant electric field. The electric field due to this positively charged sphere without any cavity, this is without any cavity, plus the electric field due to this cavity having opposite charge density, right? So like that you can calculate at any point. So that is one approach. The second method we used previously also, like in the moment of inertia calculation and in gravitation also. Like suppose in gravitation, suppose this is a sphere of mass m and from this certain part is removed here. Now a point mass is placed at this point here, right? Now if suppose if I ask what is the gravitation force acting on this due to this remaining sphere, that means sphere with a cavity, then generally what we will do is here the force on the force due to this remaining is equal to, we can write as force due to original sphere, that means without any cavity, minus force due to removed part, right? So that means the force due to this remaining sphere we can write it as force due to original sphere minus force due to the removed part. That means we calculate the first due to this force due to this sphere without any cavity. That is our force due to original sphere. and we calculate the force acting on this point due to this cavity. And as we are removing this cavity, and we remove that amount of force also. That means we subtract that amount of force also, that gives the force due to the remaining sphere. And so now like this also, now we can solve here also. The electric field due to the original sphere without any cavity minus electric field due to the cavity. And if you subtract them, then you will get the electric field due to this remaining object here. As we know very well about this method here, I am applying this method. You can solve like that also, both are different only. The initial approach will be different. That is only that difference there between those two methods. Both are finally, or from the first equation itself, both the equations are same. The assumption is different there. So that means here we need to assume this oppositely charged density there. So now let us follow our previous method. Like now I can write this electric field at that point inside the cavity, we can write as electric field due to this original sphere minus electric field due to this removed part, right? So that gives us electric field due to the remaining object or inside this cavity. So now this is our point here. We are assuming a point P here. At that point we need to calculate this intensity of electric field. Suppose I am taking this distance of the point from the center of the sphere as R1, so its vector I can take it as R1 bar, and similarly from the center C2 it is R2 bar, right? And the C1, C2 vector you can take it as C bar. I will explain that later. Now I am writing this intensity of electric field due to this original sphere. So due to original sphere means we can apply this expression. Our point is inside the sphere only, original sphere without any cavity, and then it is at a distance of R1. So we can write it in vector form like this. So rho by 3 epsilon naught into R1 bar, right? So that is original sphere minus. Now electric field due to this remaining sphere we need to calculate. That means removed part. So for this removed part also, that means we are assuming that before removing this, if this part is not removed, then force due to this part we are calculating here. So then we need to assume here also the charge density plus rho will be there. Then for this sphere the point is again inside. So again we can apply this formula here. So it is rho by 3 epsilon naught into R2 bar, right? The same thing, only the distance from the center here is R2 here, from that center of that particular sphere. And so now this is E bar is equal to rho by 3 epsilon naught, you can take common, then R1 bar minus R2 bar, right? Now R1 bar minus R2 bar value we need to write here. So the R1 bar minus R2 bar value can consider by using this triangle C1 C2P. If the triangle is considered, so from triangle C1 C2P, if the triangle is considered, that means I will draw this diagram here. This is C1, C2, this is R1 and this is R2. Suppose this vector I am taking as C bar. That C bar direction we are defining from C1 to C2. Now we can observe that if you apply the triangle law for this triangle of vector addition, this is the resultant of these two vectors, because these two vectors are taken in same order, right? And so I can write this R1 bar is equal to R2 bar plus C bar. From this we need C bar is equal to R1 bar minus R2 bar, you can write. Therefore, the cavity as rho by 3 epsilon naught into C bar we can write here. So now the important thing here is C is a constant value. Actually we are calculating at the point P here. So that indicates now at any point inside this cavity electric field will be same only. It only depends on this C, the distance between center of the cavity and the center of the sphere. Therefore they mention that the intensity of electric field inside the cavity is uniform electric field. Uniform in the sense constant electric field will be there. So at any point it will be same only. So at any point the electric field will be same. So at any point electric field is same, that means uniform electric field will be there. And it depends only on the distance between center of the cavity and the center of the sphere. So therefore I can write inside cavity field is uniform, field is uniform and it is along from C1 to C2. If rho is positive, that means if charge density is positive, then it is from C1 to C2. If it is charge density is negative, then it is opposite direction you will get here. So that is the intensity of electric field inside the spherical cavity. Important calculation, and you need to remember actually that formula, rho by 3 epsilon naught. So you need to remember that it does not depend on the radius of the C2 or radius of the C1. It only depends on this distance between those two centers there. That means it only depends on the C value here. C and charge density. Charge density will be uniform. So that means electric field at any point inside the cavity will be same, and it only depends on the distance of center of the cavity and the center of this sphere. So only depends on the C value here. That means its magnitude we can write as the electric field magnitude inside the cavity. I can write this magnitude as rho by 3 epsilon naught into C. Just we write the C as the distance between those 2 points here. So it is the electric field inside this cavity. And even if they ask, suppose if you are taking the second method, that means first method, by assuming this as positive charge density and this as a negative charge density, and we are combining them. The only difference is in this equation. Then we write this as electric field is equal to electric field due to this complete sphere plus electric field due to this cavity, that means the removed part. We add them because there we are combining them, so we should add them. And so now this term we need to write this as rho by 3 epsilon naught into R1 bar plus, now we are assuming this sphere is having in the first method, this sphere is having some negative charge. So negative charge means then electric field and R bar both are opposite in direction. So that we need to take the negative sign here. Minus rho by 3 epsilon naught into R2 bar we need to write here. So this is only the difference. Then from the next step onwards, the same thing you will get here. So whether you are solving by that method or this method, both are set. So as we know already this part, in moment of inertia we used that when certain part is removed from that, the moment of inertia of the remaining object we calculated like this. And then like the gravitation also we solve some problems based on this. And so then you can follow this method. Both the methods are same only, just initial approach will be different. Initial assumptions will be different there. And so that after this the remaining calculation is everything will be same in both the methods, right? And there will be some problems based on this. And even in this, and here the important thing you need to remember is, due to this remaining part we are calculating electric field inside the cavity. Even if they ask outside the cavity or outside the sphere, our calculation will be same. Suppose if they are asking at this point here, right? So even if they ask outside, our calculation procedure will be different, but these two expressions are not valid, because this expression is valid only inside. This rho by 3 epsilon naught into R you can write only inside the sphere. You can't write for the outside, because now if you consider a point P outside, this point is becoming outside for both cavity as well as for the original sphere. So this method is same, I am saying. The method is same, the original electric field due to the original sphere minus electric field due to the removed part we need to write. But this formula you can't substitute. Outside formula. Our outside formula is nothing but kq by small r square formula we need to write here. So then kq by small r square, and similarly this is some, if you are taking whole charge as capital Q, and this you may consider it as a small q. That means what I am saying is, if this I am taking as capital Q, the total original charge, and this part you may consider it as a small q. Then in that case at this point if I want to write here, then that I can write it as K capital Q by small r square, where small r is the distance, or R1 let it be. R1 is the distance from the center of the sphere, minus K into small q by R2 square, where R2 is the distance from C2. And small q and capital Q value you can calculate. If rho is given, you can substitute in terms of the rho here. That means even if it is outside or inside the cavity, our procedure will be same. But only if the point is outside, electric field outside formula we need to write. If our point is inside, then electric field inside the formula we need to write. Right? Got it? So this is the electric field inside the cavity. In one of the previous IT, directly they asked about this formula here. What is the electric field inside this cavity and how it depends? Multi-correct answer type, whether it depends on R1 or that means A or B or C. It only depends on that C values, right? And even if they ask outside, then this is the procedure here. The same process, but only these expressions are not valid. We need to take outside formula here. And there will be some other problems based on this. So I will explain after discussing this spherical cavity also. Sorry, cylindrical cavity also. So the same process will be there for the cylindrical cavity also. But only that formula is different here. Intensity of electric field inside the cylinder is different. What is the formula for inside the cylinder? So let us say this electric field inside a cylindrical cavity. So we'll change the marker. So inside a cavity, cylindrical cavity. That means here I am taking the situation like this. This is a long cylinder. Suppose that this is the axis of this cylinder and so that its radius is A. Now here in this it is having some volume charge density here. This is totally having some volume charge density. In this now I am taking a cylindrical cavity here. A cylindrical cavity is made like this. Now this is a removed part. This part is not there in this. This is a empty space will be there here. Now this radius I am taking it as B. And the distance between the center of this axis of the original cylinder and axis of the cavity as C. Got it? These were the dimensions, same as that of our spherical cavities. I am taking the same notation so that you can remember them easily, right? A is the radius of the original cylinder and B is the radius of the cavity and C is the distance between axis of the original cylinder and axis of the cavity. And now we are assuming that the cylinder is having some charge density rho here, volume charge distribution this is. This total charge density rho will be there here. Right, it is having some charge density rho. Now we need to find intensity of electric field at any point inside this cavity. And now this is the original view here. Now I am drawing the top view. When you are observing from the top view, then we can write it as when you are observing from the top, you can observe the situation like this. It appears like same as that of our previous cylinder, previous sphere, spherical cavity. So this is A. Now this is our B. And this is the C. So now again we take some point P here, say the distance of R1 from this and R2 from this, right? This is the top view. When you are observing from the top view of this cylinder here, when you are observing from the top, then it appears like this. And it is having same volume charge density here. Right? And so now the same approach, the same process, everything will be same. The only difference is intensity of electric field inside the cylinder. So inside the cylinder our formula is, we derived already in the previous class. So like it is rho by 2 epsilon naught into R you will get, right? In vector form if you are writing, then you can just keep bar. And so now here, the same process, everything will be same. So directly I am writing here. Only the difference is this equation. So the electric field inside the cavity we can write it as electric field due to the original cylinder minus Substitute those expressions and simplify that. That means I can write this as electric field inside this cavity is equal to, due to the original sphere I can write as rho by 2 epsilon naught into A, that means R1 bar, sorry this is R1 bar minus rho by 2 epsilon naught into R2 bar, right? Now therefore this can be simplified as electric field inside this cavity is equal to rho by 2 epsilon naught into R1 bar minus R2 bar. And again the same calculation you will get here. That means you can consider the triangle like this. Suppose this is our point P, then R1 bar and this is the R2 bar. This is C1 and this is C2 here. So I can consider this as some C bar like this. Therefore from this you can write this C bar as, from this diagram you can write this C bar as R1 bar minus R2 bar you can write. Therefore this electric field inside the cavity you can write this as rho by 2 epsilon naught into C bar you can write. And so in magnitude we can write as electric field inside the cavity is equal to rho by 2 epsilon naught into C you can write here. That means now this field is also constant only. Electric field inside the cylindrical cavity is also constant, and it also depends on the distance between the axis of the cylinder, original cylinder, and axis of the cavity only, right? And then the direction of electric field is also same. If it is positive, then it is from C1 to C2 here. This is the direction of this electric field. And so then that means, so inside cavity, electric field is uniform, and it is from C1 to C2 if rho is positive. That means if charge density is positive, then it is from C1 to C2. If charge density is negative, then it is in opposite direction here. So I can write this field lines, and for the previous one also draw the field lines diagram there so that you will get the clarity about that. So that means here the field lines is nothing but, so I will draw this diagram here. I will rub this. So that means field lines you can represent like this. So that you can understand how the field is. So then our field is, this is having some positive charge density we are considering here. This is having, total I am representing like simply plus rho, positive charge density. Now the electric field is, we are saying from C1 to C2, right? And so that this electric field lines will be like this. So the electric field is from C1 to C2. Uniform field will be there like this. Equidistant and uniform field. So uniform field can be represented like this. And draw this diagram for the spherical also, for the spherical cavity also. Because you will get the same diagram. And this is again the top view of the cylinder here. For the sphere, it will be the diagram for this. So that means same diagram you will get for this both cylindrical and spherical. For the cylindrical, it will be there throughout this. If the cavity is like this, cylindrical, then everywhere these lines will be there. And so then that is a radar, that means field lines inside this cavity here. So field is uniform, field will be there inside this. Got it? So that is the expression for this electric field inside the spherical cavity and inside this cylindrical cavity. Now there will be some problems based on this spherical cavity or cylindrical cavity. So let us see those problems now. I will explain some of those problems, then you can solve the remaining problems. So here let us write one problem here. Two identical spheres each of radius r are having uniform charge density plus rho and minus rho respectively. Plus rho and minus rho respectively. Assume that these two spheres are overlapping on each other. Overlapping on each other as shown in the figure. Overlapping on each other as shown in the figure. Find intensity of electric field. Intensity of electric field at any point in the superposing area or in the superposing space, superposing volume. So at any point in the superposing space. So at any point in the superposing space. So it's a previous question only. And it's again the same, either a cylindrical cavity like such a cylindrical cavity or this type of questions will be there in magnetism also. So now here they say these two spheres are superposing here. The same, almost the same questions will be there in magnetism. There generally those are cylindrical conductors there we consider here, current carrying conductors. So now see here the same process. So this is the superposing area here. I am taking one point P here. Say at a distance of r1 bar from the center of the first sphere and r2 bar from the center of the second sphere, right? And now let us write the electric field. Now you need to observe this, that point P will belongs to this first sphere because it is inside that sphere, and at the same time that point P is also the internal point for the second sphere, right? So for both of them we can write the inside formula. That means that now the resultant electric field at that point P is nothing but electric field due to the first sphere plus electric field due to the second sphere. Just we are adding them. Here nothing is removed, right? Just those two spheres are superposing on each other. Then resultant electric field we are writing. Electric field due to the first sphere plus electric field due to the second sphere. And so that then this can be written as this net electric field is equal to, again same formula we can write here, rho by 3 epsilon naught into R1 bar plus, now this is the negative charge density. So negative charge density means why we are writing, due to this positive charge density, electric field will be along this direction only. Like say I can represent like E1 like this. So E1 and R1 bar both are in the same direction. But electric field due to this negative charge density will be E2 direction will be like this. So E2 bar will be along this direction here. That means towards the center. R2 bar is added from the center. E2 bar will be towards the center. That's why we need to take the negative sign there. So minus rho by 3 epsilon naught into R2 bar we can write. That is our E2. So whenever this negative charge density is there, you need to remember this this point here. So you need to take the negative sign in vector form. Therefore this net electric field again rho by 3 epsilon naught I am taking common, then R1 bar minus R2 bar. And we know about this calculation very well, that R2 bar minus R1 bar is nothing but you will get C bar. This is R1 bar and R2 bar. So this is C1 and C2, where C bar is the distance between those two centers. Therefore that C bar we can write as R1 bar minus R2 bar we can write. Therefore this net electric field we can write as rho by 3 epsilon naught into C bar we can write. So this is a net electric field. So that depends again only on the distance between those two centers. It doesn't depend on the distance from the C1 or distance from the C2. And here again the direction is also the direction of electric field lines also from C1 to C2. That means if you want to write the field lines, again uniform field will be there. Same as that of our cavity we are getting. Got it? Because this behaves like a cavity only. Because here net charge in this region is nothing but 0. That is nothing but first method what we are discussing there. We are assuming positive and negative charges inside this cavity. We are assuming a negative charged sphere is placed there. So that net charge in that region will become 0. So here also the net charge in this region is becoming 0. So that it behaves like a cavity only. And so now the electric field lines will be like this. Just I am representing the electric field lines. So throughout this volume, the electric field lines will be there like this from C1 to C2. So that is a uniform field will be there, which depends only on this C, distance between those two centers. right? So that is one problem. So note that. I will explain the next problem. So next problem just I will explain so that you can solve by yourself this cavity problems. So here I can write this as this is a sphere of radius r having some uniform charge density rho. Now here having some charge density rho, and there is some cavity here, spherical cavity of diameter r is made here. Suppose this is our center C and this point is B, and here I am taking a point A here, right? So now this is our cavity. So now in this question, write that question actually. A spherical cavity of diameter r, a spherical cavity of diameter r is made in a sphere of radius r, is made in a sphere of radius r having charge density rho, charge density rho. Find electric potential at the points A, B and C. Electric potentials at the points A, B and C shown in figure. Next question. If an electron of mass m, if an electron of mass m and a charge minus e is released from the point A, find time taken by the electron to strike the surface of sphere, surface of cavity, to strike the surface of cavity, and also find with what velocity it strikes the surface of cavity, with what velocity it strikes the surface of cavity. Neglect gravity, that means we are not considering any gravity here. So these calculations you can do, just I will explain for one of that. So then generally while writing for this potential, you may consider the charges there. Like suppose I am taking this capital Q is a charge present in this sphere without cavity, total charge, and a charge is present in this charge in the sphere of radius r by 2, right? And so now here I can write like this. Suppose I am writing potential of point C here. The potential at that point C I am writing. And so now the potential due to the original sphere, same process, minus potential due to the removed part, right? If capital Q is the charge present on the original sphere I am taking. And so then this can be written as 3kq by 2r. So why we are writing this? Because for the complete sphere, that point C is the center of the complete sphere. At the center of the complete sphere, this potential is given by this expression. We already know this. We derived an expression for potential at any distance, at any point inside the solid sphere, and this is at the center, right? And now similarly, this point, how this point is for this cavity. For this cavity, this point is on the surface, right? And so then this is nothing but minus k into on the surface means kq by small r, capital R we need to write. Here r means r by 2, radius of that sphere we need to write. That means we are treating this as one surface, and so for that surface this is our point C is lying on the surface. So that formula we need to calculate. And capital Q and small q values we can write here, rho into like 4 by 3 pi r cube and a small q is rho into 4 by 3 pi r by 2 whole cube. Right? These are capital Q and small q values. So that is point C here. You can simplify that, you will get the potential at point C. The same process we need to write for this point B and point A also. Right? For point B, it is for this original sphere, it is just at a distance of r by 2 from the center. So potential inside that original sphere we need to write. And for the cavity, that point B is the center. So then 3 small k q by small r we need, that means 2 into r we need to write. 2 into r is nothing but r by 2. Here the radius is r by 2 we need to write. The same process for the point A also. Got it? So potential at that particular point due to the original sphere minus potential due to the removed part we need to write. So for the original sphere where that point lies, and for the cavity or for the removed sphere where that point lies. So just you need to observe that and corresponding formula we need to write there. So I think you can calculate the remaining points B and C. You can simplify this further by substituting this small q and capital Q values and simplify solve the remaining parts also, right? And let us come to the next question. So now the next question is, here we are releasing an electron here. So if you release an electron, what will happen? Here gravity is neglected. So if you release an electron there, what will happen? So if you release an electron, the electron will experience some force, because here the direction of electric field is along this direction. The direction of electric field from center of the sphere to center of the cavity, because it is positive charge only. So the electric field will be along this direction. So then electron will experience a force in opposite direction here. So the force acting on the electron will be E into E. That will be in opposite direction because it is a negative charge, and so force acting on the electron will be opposite to that of electric field, and so then a force will act like this. And because of that force, the electron will start accelerating. So it starts accelerating from here to here. And so then they are asking just a time taken. So I am taking the second part of this problem. The first part I think you can do the remaining these two calculations. Now I am going to the second part. So that means force acting on the electron is E into E. And where E value is we already know. Where electric field is rho by 3 epsilon naught into C we need to write. Electric field inside the cavity. So here C is nothing but distance between center of cavity and the center of the sphere. So the distance is nothing but r by 2 here. So that means it is rho r by 6 epsilon naught. Got it? This is the electric field. And so substitute there. Therefore I can write MA is equal to rho into r by 6 epsilon naught into this is E. Now from this you can write acceleration. Rho r into E by 6 m epsilon naught. Right? Now we can observe that this acceleration is a constant value. So acceleration is constant. As the field is uniform, then you can conclude that acceleration is a constant. So field is uniform, field will be there. So as a uniform field is there, that means acceleration is constant in the sense. Now we can use S is equal to half AD square term you can use. Because the particle is moving with the uniform acceleration. And initial velocity is 0. We are releasing from rest here, so that you can write initial velocity is 0. Right? And so now it has to travel a distance of from here to here. Then it will strike exactly the opposite point, which is nothing but C. So then it has to travel a distance of R. So R is equal to half into A is nothing but rho R into E by 6 epsilon naught into M into T square. Therefore the T value we can write as under root of 12 M epsilon naught by rho into E. So that is the time taken there. Time taken to travel from one end to other end. And if you want to calculate velocity, so the velocity you can calculate either by using v square minus u square is equal to 2as, or you can also use it as v is equal to u plus at. Because we already calculated the t value. So either you can use v square minus u square is equal to as, or v is equal to u plus at we can use. So then as we know the t value, just I am using this equation there. So then A is nothing but rho into R into E by 6 m epsilon naught into T value I am substituting from this. So I am using this equation there. So then it is 12 into m epsilon naught by rho into E.
So then you can simplify further, then you will get the velocity with which it strikes that other surface, that means other point here. So it is a way of calculating this problem here. Note it. And there will be a lot of problems basing on this cavity. So I will give some of those problems and try those problems. See, in the same problem, for example, instead of releasing the electron from the point A, I am releasing it from another point here. Note this and find the time taken and velocity. Second part of this problem. Suppose I am releasing this particle from here. This is C, B and this is A. We are releasing from this point, suppose say D. This is our point D, which makes an angle of 45 degrees here with the line ABC. So we are releasing the electron from rest here. An electron is released from this point here. So just mention it as the next question. In the above question, if electron is released from the point D as shown in the figure, then draw this diagram again. In the above question, if electron is released from the point D as shown in the figure, find time taken by the electron to strike the surface of the cavity, for the first time, and with what velocity it strikes the surface of cavity, So here I mentioned for the first time in the sense, for example, if any type of like elastic collisions are taking place, here it may undergo this multiple collisions, multiple times it may strike the surface there. So for that I am taking it as for the first time it is colliding. For the first time it is hitting that, we need to find that, right? So next. So now I am taking a cavity like this. This is a sphere here. Now I am taking a cavity like this. This is suppose say now r by 2 and this is r. Now our point is somewhere here. A, next B is here, next C is somewhere here. So we need to find phi, and this is having some charge density rho, let us consider. As shown in the figure, next question, this is, as shown in the figure, a spherical and a concentric cavity of radius r by 2, a spherical and a concentric cavity of radius r by 2 is made in a sphere of radius r, made in a sphere of radius r having charge density rho, Then find intensity of electric fields at the point at a distance smaller from the center, find intensity of electric field at a distance smaller from the center when r is less than r by 2, that means point A, and r by 2 less than or less than capital R, that means point B, and the third one is when this capital R is less than this smaller, that means outside. Now in the previous problem the cavity is not concentric, right? Now here I am taking a concentric cavity. Then we need to answer about this point intensity of electric field at the point A and point B and point C. Can you say at point A, what is the intensity of electric field at the point A? Either you can apply our formula for the cavity what we derived, or generally also you can say. If you apply that formula for the cavity, our formula is rho by 3 epsilon naught into C, right? Our formula is intensity of electric field inside the cavity is rho by 3 epsilon naught into C we are writing, where the C is distance of the cavity, center of the cavity from the center of the sphere, right? Now in this problem the distance is 0, this value is 0, and so that intensity of electric field at the cavity, inside this cavity will be 0, right? Got it? That means there is no electric field at any point here. So if the cavity is concentric, then electric field inside this cavity will be 0. That simply you can assume that this sphere is made up of a thin spherical shells. That means you can consider this thin spherical shell like this. Such a lot of thin spherical shells you can consider here. For each thin spherical shell, this point A is lying inside. And by using Gauss law and previously also we know that inside the spherical shell intensity of electric field is 0. And so that due to all these shells from starting from this R by 2 to R, for all the thin electric thin shells, electric field at this point will be 0 only, right? So like that also we can explain, or by using this formula also we can write here. Therefore I can write this intensity of electric field at point A is 0. Now see how to find this second condition here. This is the first condition here, when R is less than R by 2. Next, suppose I am taking the second condition here. Like a second condition means R by 2 less than R less than capital R. It lies at the point B I am taking here. And so now we need to apply our Gauss law. We need to follow our procedure. Gauss law we need to apply here. So that means integral of E bar dot dA bar or ds bar is equal to 1 by epsilon naught times q in, right? And so now directly I am substituting those values here. E into dA is nothing but here again that E bar and dA bar will be along the same direction here. At point B if I consider dA is along this direction, dA is also along this direction. So then E into 4 pi r square I am writing here. And this term is we know already. Next the term we need to calculate here. 1 by epsilon naught into this side also rho into volume we need to write. Here rho is constant only, so no need of any integrations here. So directly we can write it as rho into volume. So the charge is present only within this volume here. So that volume only we need to write. So I can write that volume as 4 by 3 pi small r cube minus 4 by 3 pi r by 2 whole cube. Got it? Only between these two, but from r by 2 to small r we need to write here. This is our smaller value. Only that volume we need to write here, because only charge is present only within this part here. Within this part only charge is there. This part is cavity, and so you can simplify that. Therefore E is equal to rho by this 4 pi. I think you can take 4 pi common and you can cancel that. Rho by epsilon naught into 3 epsilon naught into r square into here if you take that 4 by 3 common, then r cube term will be there, minus here that is r cube by 8 term will be there, right? 4 by 3 pi we are taking common, 4 pi will be cancelled on both sides, 3 will be remaining here. So this will be our expression here. You can write r inside, and if you want you can simplify that. So this electric field at the point B there. Similarly calculated the point C. Point C will be easy only. You can write outside formula for the electric field due to the complete sphere minus electric field due to this point we can write here at the point C if you want to write. Or you can calculate the charge enclosure here. Just similar to this you can write charge enclosure. Then here this term will changes from r cube until here r cube minus r by 2 whole cube we will get. Directly like this also you can write there. So that is our choice. So similarly find at the point C. So these are some problems based on this cavity here. So all these problems you can solve easily if you understand these concepts here. Inside the cavity, and that is rho by 3 epsilon naught into C, where C is the distance from center of the cavity to the center of the sphere. And if the charge is positive, then it is from the center of the sphere to the center of cavity, that is the direction of the electric field. If it is negative, it will be opposite direction. And if the cavity is concentric like this is important here. If the cavity is concentric like this, then electric field at any point inside will be 0 only. inside that cavity will be 0 only. And then if any intermediate point, if it is like this, then we need to calculate like this. And at point C, as I said, you can solve easily. Here just only here these values will changes here. That is nothing but here charge enclosed is nothing but capital R cube minus here this term will be small r cube will be there. Only these two here change will be there in that for point C here. Capital R cube we need to write there at point C if you want to write. Got it? So then practice the problems given in the Singhes based on this cavities and based on the Gauss law applications. And in the next class we will discuss some more applications of this Gauss law. Thank you.